Yeah, good afternoon, students. Yesterday we discussed something about suspensions. Again, now also we continue the topic. In today's session, aim of the session is to familiarize the students with the concepts of suspensions, and objectives of the session are demonstrate the dispersed systems and list out the various suspensions and characteristics of these suspensions. Coming to the outcomes of the session, at the end of the session the student is able to describe the factors affecting the stability of the suspension and define the calculate to useful sedimentation parameters like sedimentation volume and degree of flocculation. Yeah, in the previous class we studied about different classifications. Those are first one of the classification is classification based upon the electrical properties of the solid particles that we have disposed in the solution. Depending upon the electrical properties of the solid materials in the suspension, these are classified into two types. Those are deflocculated suspensions and flocculated suspensions. First we will see with the deflocculated suspensions. Here the deflocculated suspension, the particles are present in the form of individual particles. Whatever the material solid particles are converted into suspension, all the solid particles they will behave like individual, and when they are settling to the bottom of the container, individual particles will get settled into the bottom of the container, and rate of the sedimentation is slow. Why? Because the particle size of the suspended particle is very less. Due to the less particle size, the rate of sedimentation will be slow, which prevents entrapping of the liquid medium, which makes it too difficult to redisperse. And this phenomena is called as caking or claying. Here if you see a deflocculated system, in the deflocculated system, we are going to prepare the suspension. All the particles present in the suspension are having different sizes. Different sizes means we are not sure that each and every particle is lying between 1 micrometer, 2 means like that. Very narrow particle size may not be assured. Here there are different sized particles will be there. Some particles will be larger particles and some particles will be finer particles. If you take this suspension with the different sized particles, so what will happen? Slowly the larger sized particles will settle down first, and after the larger particles settle down, slowly smaller size medium sized particles will come and settle on the top of the larger particles, and whatever the finer particles are there, those finer particles will packed in between the gaps that are present in between the larger particles. See like this. Here if you have taken the suspension particle size, these are larger particles. These larger particles, while they are settling to the bottom of the container, the larger particles they will settle by maintaining some gaps in between the particles. Now medium sized particles, whatever they are present, they will settle in between the larger particles. If finer particles are there, those finer particles will come and settle in between these gaps, void gaps that are present between the larger and medium sized particles. So what will happen? The packing will be very close to each other, and if you prolong the condition for longer periods of time, this will cause a hard cake formation by the solid particles. So the disadvantage with this deflocculated suspensions is, if you allow the suspension to settle, these deflocculated suspensions will form cake formation. Cake formation will be there. Whenever the suspension is forming a cake, it is not possible to redisperse the cake, hard cake that is formed. In the deflocculated suspension, larger particles settle fast and smaller remain in the supernatant liquid, so supernatant appears cloudy. And coming to the flocculated suspensions, and these flocculated suspensions, the particles, smaller particles in the suspension, they will forming a loose aggregate like structures. 3 to 4 smaller particles, they will form a floccule like structure. A loose aggregates will be formed. This is one floccule and this is another floccule. Cluster formation will be taking place by the molecules. Due to the formation of the cluster like structure, these flocks are having larger particle size, and whenever these flocks are formed, see this is one flock and then another one is like this group of floccules, they are formed and they are settling to the bottom of the container. Whenever the floccules are settled to the bottom of the container, those floccules will be loose aggregates and the aggregation of the floccules will be looser in nature. At the same time, they will form a loose arrangement in the suspension sedimentation. So, whatever the sediment that is formed, the sediment will be easily redispersed when you apply a shaking or hesitational force on the system. Now here floccule size is porous in nature and they will settle down to the bottom of the container fastly, but though they are sedimenting fast and at the same time they will redispersed when you apply some amount of hesitational force. Coming to the differences between flocculated suspension and deflocculated suspension, particles form light fluffy conglomerates called flocks, but in case of deflocculated suspension, the particles in the suspension remain individually, and the flocks are group of particles. Rate of sedimentation is fast, and here deflocculated system, rate of sedimentation is slow. Formation of the sediment is fast. Formation of sediment takes long time, and if you take the redispersibility of the system, the redispersibility of the system will be more in case of flocculated suspension and the redispersibility is less in case of deflocculated. Why? Because the hard cake formation is going to take place in case of deflocculated suspension, and sediment volume will be high in case of flocculated suspension, sedimentation volume will be small in case of deflocculated suspension. And the supernatant, whenever those particles, all the particles are sedimented to bottom of the container fastly, the sediment supernatant liquid will be clear in nature in case of flocculated suspension, and the supernatant liquid remains cloudy in case of deflocculated suspension. And redistribution of the sedimented particles will be very easy, and with a small amount of shaking force also flocculated suspension can be redispersed, but redispersion is not possible in case of deflocculated suspension due to the formation of hard cake. This is the proper view and theory of suspension. Coming to the theory of suspension, here this theory of suspension will be useful for the formulator to formulate a proper and stable suspension. First one is, under this we need to consider so many points. Those are to select the ingredients that are most appropriate for the suspension. Here the theories of suspension will be useful to select the proper ingredients to form a most appropriate suspension, and to use available mixing and milling equipments, and it is based upon following theoretical for making the suspension we need to consider so many theoretical considerations. What are they? First one is wetting of the particles. Next one is particle interaction, electrokinetic properties, aggregation of the particles, Brownian motion and sedimentation. And we need to control the particle size. How can you control the particle size? Here particle size of any suspension is critical and must be reduced within the size range. Too large or too small particles should be avoided. The particle size should not be too large, it should not be too small. Why? Because larger particles will settle faster at the bottom of the container. Particles with greater than 5 microns impart gritty texture to the product and also cause irritation if injected or instilled into the eye. If you have taken particles greater than 5 microns, they may block the needle. Means in case of, if you want to prepare any parenteral suspension, in that case you have to consider these many points. Okay, too fine particles will easily form hard cake at the bottom of the container. Just now we discussed about hard cake formation. And next one is, another point we need to control is wetting of the particles. Here, why wetting of the particle should be considered for the preparation of suspension. Say for example, you want to prepare a suspension, you have to take different types of ingredients, so called some talc, zinc oxide, magnesium. These are the different ingredients which are having hydrophilic properties, and some hydrophobic materials like sulfur, charcoal, like that. Some types of different materials we need to combine together and we need to prepare them, make them into a suspension. In such cases, if the material is a hydrophilic material, it will be easily wetted by the solid surface or will be easily wetted by the water or vehicle. If you have taken any hydrophobic material, in such cases the surface of the material will not be wetted by the liquid vehicle. So what will happen if the particle is not wetted by the liquid medium? It will not distribute throughout the medium that much easily. So what will happen immediately? Whatever the solid material you have added to the liquid medium, it will be floating on the surface of the medium. So it is not possible to disperse the solid particle in the liquid medium. So to impart the dispersibility to the particle, we need to make sure that the particle should be wetted by the liquid medium. To improve the wettability of the particles in the liquid medium, we have to use some wetting agents. These wetting agents, what they will do? They will remove the air that is entrapped between the void spaces. By that way, these wetting agents will impart the wetting property to the solid substances. Examples for this wetting agents are glycerin, or you can use polyethylene glycols also, or otherwise sometimes you can use surfactants like twins and spans. What are the reasons for poor wetting? Hydrophobic substances, high interfacial tension, air entrapment, high contact angle. These are the reasons for poor wetting. Hydrophobic substance. If the substance is hydrophobic substance, the contact angle will be very much high, and high interfacial tension will be there in between the solid particle and the liquid medium. If the solid is entrapped with the air, in such case also entrapment of the air also causes poor wetting, and high contact angle also leads to poor wetting. How can you overcome the poor wetting properties? How can you impart wetting in such cases? If you add any wetting agents like glycerin, polyethylene glycols, they will impart wettability by replacing the air that is entrapped between the void spaces present in the solid part, in between the particles. And surfactants like spans and twins can be used as wetting agents, and these surfactants, they will reduce the interfacial tension between the two phases. By that way, they will reduce the poor wettability of the preparation. Here finely powdered particles are more entrapped with the air, so do not get moist even when driven below the surface of the suspending medium. Here particles, very finely divided particles, are less prone to wetting. So entrapped air will be there. In such case, if you add some amount of wetting agent, it will be useful. Surfactants are highly beneficial in reducing the interfacial tension between solid particles and vehicle while creating the suspension, and decreasing the interfacial tension increases wettability and deflocculation by lowering the advanced contact angle with displacing air from the particles surfaces and lowering the advanced contact angle. There are some different points. Just now I explained with the glycerin and polyethylene glycols and surfactants. Next one is we need to consider the sedimentation properties. Here what are those sedimentation properties? The sedimentation properties can be explained with the help of theory of sedimentation. Here the theory of sedimentation indicates sedimentation means settling of the particles or floccules occur under gravitational force in the liquid's dosage form. Here you take in the suspension. Suspension means we have to take a liquid medium. Within the liquid medium, the solid particles will be distributed, right? Here the solid particles will be distributed in the liquid medium. Now the solid particles are distributed. Here each and every solid particle is having its own particle size, own diameter and its own weight also. And now depending upon the particle size of the particle, the particle will be drawn towards the bottom of the container due to the gravitational force acting on the each particle. So what will happen? These particles will move to the bottom of the container according to their size and weight. So we need to control this particular sedimentation process. So what we have to do? We have to consider the points whatever that are given. Here the velocity of the sedimentation can be expressed by Stokes equation. Stokes equation, V is sedimentation, velocity of the sedimentation is equal to d square into rho s minus rho naught into g by 18 eta naught. Here d is the diameter of the particle, r is the radius of the particle and V sediment is the sedimentation velocity in centimeters per second, and rho is the density of the dispersed phase and rho naught is the density of dispersion medium, g is the acceleration due to gravity, eta is the viscosity of the dispersion medium. Here if you see the Stokes equation, diameter and radius, diameter is present in the numerator. Here numerator, whenever the numerator value is increasing, V value will get increased. Means if you increase the d value, what is the equation? V sediment is equal to d square into rho s minus rho naught into g by 18 eta. Here d is the diameter of the particle. The diameter is present in numerator. If the diameter is increased, say for example you have taken diameter of the particle as 2 microns initially. 2 microns is present. 2 into 2 here, 2 square indicates 4. You have doubled the diameter. D is equal to 4 microns now. Just place the 4 in place of 2. 4 square, that is the numerator value is increasing exponentially if you increase the particle size. Numerator value is increasing exponentially means what will happen to the total fraction value? Fraction value also increases, means the sedimentation volume value also increases if you increase the d value. So means d indicates diameter, that is particle size is increased, doubled the particle size, the sedimentation will be exponentially increased more than the double rate. Means so what we have to control, main controlling parameter is diameter. Diameter of the particle should be controlled, means diameter should be less. If you reduce the particle size is reducing, the numerator value is reducing, at the same time total fraction will be reducing, by that way it will leads to less sedimentation. Okay, and second parameter, that is density difference between the particle phases. Rho s is the density of the dispersed phase, rho naught is the density of the dispersion medium. Say for example, dispersion medium is water, always the rho value is 1. Okay, if you have taken the density of the material is 1.1. Density of the material you have taken is 1.1 gram per cc. Now what is the difference between two? 1.1 minus 1, it is of 0.1, where density difference is very low. So what will happen? The fraction value is not that much increased. So volume of sedimentation will not be that much affected by the density. If the density difference is very much high between the dispersed phase and dispersion medium, this will also influence the sedimentation value. And next, third parameter that you need to consider is eta naught, that is viscosity of the medium. Here viscosity of the medium is present in the denominator. Now viscosity, initially you have taken 2 centipoise as viscosity, or say for example 12 centipoise. Now the total value will be 1. Say for example the numerator value, total numerator value is 120. Okay, and now you have taken eta value as 12. Now this will be the case, 10 by 18 is the value, and now numerator value total 120 only, second case, and you have changed the viscosity into, what is the value? Take 24, means you have doubled the viscosity. What will happen? It is of 10. Finally the value will be 5 by 18. Among these two, which one is more? 12 by 18, 10 by 18 is more, or 5 by 18 is more? Obviously 10 by 18 is more, means if you have taken less viscosity of the dispersion medium, the sedimentation will be more. If you have doubled the viscosity, the sedimentation will be reduced to half. Means if you have increased the viscosity of the preparation, the total sedimentation process will be reduced, which this viscosity that is provided by the medium, this viscosity will restrict the movement of particles from top of the container to bottom of the container. Whenever there is any obstruction is occurring, obviously the particle movement will be reduced. So sedimentation of the particles will be reduced. Clear? And coming to the limitations of this Stokes law, Stokes equation, this Stokes equation is only useful for spherical particles. If the particle is spherical, then only this will be useful. And this Stokes equation is very useful in case of dilute suspensions only. And one more thing, if the particles are freely settling down without any collision, in such cases only the Stokes equation is useful. Particles with no physical or chemical attraction, then only this will be useful. If any particles are having irregular shape or concentration of the suspension is more than 10%, in such cases this Stokes equation is not that much useful. Next, coming to sedimentation parameters. If any case the suspension is not following any type of the properties, that is irregular in shape, and the concentration of the suspended particles are more, and they are not having any they are following some collisions and some physical or chemical attractions are there, in such cases it is not possible. So to estimate the stability of the suspension, then some sedimentation parameters are much useful. Those are sedimentation volume and sedimentation degree of sedimentation. Now here this sedimentation volume is a ratio of ultimate volume of sediment to original volume of this suspension. Here F is equal to this sedimentation volume, F is equal to Vu by V naught. Here Vu is the final or ultimate volume of the sediment divided by V naught is the original volume of the suspension before settling. Generally F values are ranging from less than 1 to greater than 1. If less than 1, F is less than 1, F value is less than 1, Vu is less than V naught. Sorry, Vu is less than V naught. If F is equal to 1, Vu is equal to V naught. The system is flocculated equilibrium and show no clear supernatant in the stranding. When F is greater than 1, in such cases Vu is greater than V naught. And sediment volume is greater than the original volume due to network of the flocks that are formed in the suspension, and so loose and fluffy sediments will be observed. Here if you see the diagrammatic representation, in case of first case, Vu initial volume of the suspension is 100 ml, V naught, Vu is 50 ml. If you calculate the sedimentation volume, F is equal to, here V naught is 100 and Vu is 50. F is equal to Vu by V naught, right? 50 by 100 if you take, it will give F value is 0.5 in the case of first one, in this first case. So what will happen? F value is 0.5, sedimentation volume is 0.5, less than 1 it is. In case of second one, Vu and V naught both are same, that is 100. 100 by 100 you will get 1. This system is called as, second system is called as flocculation equilibrium. And if you take third system, in this case Vu is 150 and original volume of the suspension is 100. Vu is greater than 100. Okay. Vu is greater than 100. So what will happen finally? If you calculate F value, 150, Vu by V naught is 150 by 100. This is of 1.5. This is greater than 1 here. So what will happen? If F is greater than 1, the total volume occupied by the suspension will be more than the original volume. Means here this will be possible in case of highly the flocculated suspension is having more than 50% of the solids. Highly concentrated suspensions, this type of arrangement will be possible. This is also a stable suspension and this is also a stable suspension and this is of non-stable suspension. Clear? And second parameter that is considered is degree of flocculation. It is the ratio of sedimentation volume of the flocculated suspension F to the sedimentation volume of the deflocculated suspension. Beta is equal to Vu by V naught of flocculated suspension divided by Vu by V naught of deflocculated suspension. Always the beta value will be 1, more than 1 generally. Okay. This is about sedimentation parameters.